So, oops, now what was that? Well, that's the. Okay, so what we're doing was we're applying what we've been at least studying to entities that move around. We're starting with just moving around. And then, of course, as is normally the case, questions come up as to, well, what about this and what about that? So hopefully most of those will be addressed. But the problem in question is we have an entity which has a location and can move and according to what is normally termed an equation of motion. And that equation of motion can be as simple or as complex depending upon the circumstances. We're looking at the simplest equation of motion, which is constant velocity. And that actually has more applicability than I had originally thought, but nevertheless, that's what we're looking at. So it's obviously not the most general, but if you start off trying to model the world, you're probably not going to get there. If you start off trying to model something a little bit more narrow, then at least you stand a fighting chance of getting there. So this is where we were, and okay, so what we had come up with was a component that I'm calling sort of the simplest mover, because this is about as simple as you can get. It's a very...
Professor, are these slides posted?
Yes, they are. They should be. There should be in the slides.
The ones I'm seeing are class 21.
Okay, if they're not, I'll post them afterwards. So if I thought I did, but I guess maybe I didn't. Okay, so here's the event graph that we came up with, and the idea is that the main two events is that we start our move, and then knowing how long it's going to take us to reach our destination, we can schedule an end move event, which is going to be when the entity arrives at its destination. Now, of course, the natural questions that come up is that what if something happens in between? Knowing what you know about how the event list works and how events are scheduled, then if, quote, something happens between the time that the entity starts its move and the time that it arrives at its destination, then that will be another event on the event list. And that will trigger some kind of state transition, which is to be defined. Currently, if this is the only entity around, then there are no other events that are going to be scheduled. Although we'll see in a moment that there will be some events. But I should try to, no. Okay, so now how does one implement this? Well, in the usual way, because this is, dead center in terms of the way that event graph methodology is constructed, and because there's a one-to-one relationship between all of the elements in an event graph component and in a SimKit model, we can very simply implement all of that in, again, what I call the simplest mover. Now, there are some convenience things here about some static variables, but those are just to make life a little bit easy. But our initial location and our maximum speed are the two parameters. Our state variables are what I'm calling the last stop location, which is the location where we stopped last. Our velocity, which could be 0. Remember, velocity is a vector, so we're representing it as a point with two coordinates. And then our current destination, which is where we're headed right now. And then finally, we need to know when we started to move. And knowing all of that, then we can determine, well, first of all, when we actually arrive, but more importantly, we can also determine through an implicit state where the entity is at any possible time. If you remember back when we were looking at multiple server queue, when we only had state variables of the number in the queue and the number of available servers, there was another variable of interest, a state, if you will, of interest, which would be how many customers are in the system. And the thing is that in terms of state variables, that was actually redundant with respect to the other two. So if you told me how many are in the queue and how many available servers we have, I could tell you how many are in the system by a simple formula. Likewise here, if you tell me when you started to move, what your velocity is, and where you were when you started, and you haven't arrived at your destination yet, then I can tell you exactly where you are at any time in that maneuver. So that's an important distinction. However, now in order to test this, one of the challenges with just this component is because the run event doesn't schedule anything, we by itself, if we just kind of instantiate this and start the simulation, we're going to get the run event and that's it. So, but when we're testing these components, we can, again, just for testing purposes, it can be convenient to kind of stick some schedules in just kind of by hand. So here's an example. So our initial location, we're going to put ourselves at minus 40, 30, our maximum speed at 40, whatever those are. The caveat on this is that when you're putting the numbers in, you need to be sure that your units are consistent. So if my speed is in miles per hour, then my distances and my locations had better be in miles. If it's kilometers per mile, then my distances had better be in kilometers, or else there's going to be a mismatch when I try to do computations. And you all remember the Mars satellite that kind of crashed because one team was using metric and the other was using English things, and they just used the numbers, and the numbers screwed it up. So okay, so what can we do now? Remember that the reset method kind of just clears out any events on the event list that are there. So what is it that we can do? Well, between reset and start simulation, let me tell this mover to move here, in this case the origin, and I'm going to tell it to not move right away, but move at time 1.5. So what I'm looking for is the right events to take place. So there's going to be a run event that happens right away. And then at time 1.5, I'm expecting to see a move to, a start move, and then at a certain time after that, I expect to see the end move. So again, that's how you make sure, try to verify that your components are doing what they are supposed to do. So again, first the purpose of printing the components just for these verbose outputs is to make sure that my parameters have actually made it inside. If they haven't, then nothing, I have no chance. Okay, so now when I start the simulation, I have the run event, and then here's the move to event, which is at time 1.5, and that's exactly what I wanted to see. Now the run event, that's going to initialize, zero velocity. Now my last stop location is my initial location. I check on that. I don't have a destination yet, so I have this not a point, and not a point is a point 2D whose coordinates are not a number. So, and the advantage of that is that if I'm in a state where I don't have a destination and I'm trying to manipulate this point somehow, then I'm just going to get not a number stuff. So, and that's what I want if I'm manipulating it in a situation where I shouldn't be doing. Okay, so here now we advance time to 1.5. We have the move to. My current destination now goes from not a number or not a point to the origin, which is where I was heading. And then that schedules my start move event with 0 delay. Again, that's what I'm looking for because that's what this scheduling edge says. And then the start move. Now my velocity, and I could verify this by hand, but my velocity, at least does it pass a little bit of the sniff test? Is it at least in the right direction? And remember, my x coordinate was negative, my y coordinate was positive, and that means if I'm heading towards the origin now, my velocity is going to be positive in the x direction and negative in the y direction. Okay, so that's a check. And if you, if we kind of check this out by hand, so if we have 32 squared plus 24 squared, and then take the square root of that, then we get 40, which is our speed. So there's a check on that. And then finally we have the end move event. So the start move time is now, was 0, and now it's 1.5. And then this says that it's going to take us 2.75 to get there. Once we arrive, then now our velocity, our last stop location is now exactly where our destination is. Our velocity is also 0, and now we don't, since we've arrived at our destination, our current destination is not a number. So that is, at least a cursory verification of our implementation of our of our simple mover.
What was the implementation to turn the velocity into a vector?
Pardon me?
What was the implementation to turn the velocity into a vector?
By defining it as a point 2D. So a point 2D is a two-dimensional thing, and so we define velocity as a point 2D and not a scalar. Because if we're trying to do the equation of motion, we need the vector. That.
Yep. I was trying to make sure I understood how it was, because the input in the run was just double.
That's correct. So what we're saying is, good point. So we're saying that this is the speed at which you're going to be traveling. And speed is a scalar. Velocity is a vector. So what that means is that if I'm trying to go in a particular direction, then the magnitude of that vector needs to be my speed, which in this case is 40. And that was a little calculation that I did to verify that this velocity was in fact, at least had the right magnitude.
And the system is calculating it by something you define in the simple mover class, or is it like a back-end thing? I'm just trying to understand the mechanics of, so I put a float, or I put a double into the run event. Where does it know, where is the code that tells the system I need to turn this into a point 2D and how to do that?
Well,
I understand why it ends up as
it comes from the event graph. So here in the event graph, this is the equation for the velocity.
Okay, so we just need to make sure that our simplest mover class has that conversion.
Yes. Yeah. In other words, you need to, if this is the state transition for velocity, it says this on the right-hand side is what your velocity needs to be. And again, what is that? That is the vector from your current location to the destination, turned into a unit vector by dividing by its magnitude, and then multiplying by the speed to give it a vector in the right direction at the right magnitude. And that, that took a little bit of doing in the method. Let's see, where was it? Yeah, here in the start move. All of this is implementing that equation. So first I have this vector that point 2D that I call temp, and that's the difference. See, I take the current destination x coordinate minus the last stop location, that's x naught, x coordinate. So I take the difference of the x and the y coordinates, and then I utilize a method of point 2D called distance. So it has a method called distance, which will give me the Euclidean distance between any two point 2Ds, or between the point 2D of the argument and the one that I invoke it on. So that's what gives me the magnitude, the norm of the vector, if you will. And then now I use the set location to take the x coordinate of this difference, divide it by the distance, and multiply it by the max speed, and that will, for both the x and the y coordinates, that will give me a vector which is in the right direction and has the magnitude of the maximum speed that I want. In other words, implementing this equation. Okay, so now that's, so what we've done so far is at least sort of verify that this is something which can actually work. But I say, well, it's not too interesting to just be able to have one maneuver like this. And furthermore, as a component, it's just sort of sitting there. So how can we make this do something a little more interesting? And by analogy to our simple mover component had an arrival event that it did not schedule, and so it needed to be listening for some arrival event. And so we're going to do something similar to that. So the idea is that we now have a component that can sort of get us from one location to another, but what the rules are, if you will, for how to get from one location to another are things which are, there are lots of different possibilities. And so if we try to put all of those possibilities into this component, then we're going to have a different one we're going to have a different mover, if you will, for every single one. So instead, the idea is to componentize the rule. And the term that I use on that is a mover manager, because it's basically managing the movement of some unit. And so the idea, the first and most natural, in my thinking, is what I call a path mover manager, and that is, the rule is that I have a set of waypoints that I want to direct my mover to go to, and when it gets to the end, I want it to stop. Okay, so that's the rule. So I'm going to have a bunch of waypoints, and I want my guy to go here, and then here, and then here, and then here, and then stop. I mean, that to me is about the simplest rule that there is. And so how can we create an event graph component that captures that? Well, first we need to know, well, what are the waypoints? Where do you want this thing to go? And so just the simplest possible way to model that would be an array of these point 2D things. So these locations are all going to be what we're using point 2Ds for. And so I'll have as a parameter an array of these things. Now, and it also turns out that, well, do I want this to be doing this right away, or do I want it to maybe wait and do something else? And so to that, I have just sort of a Boolean, which just says to start on the run. So if it's true, I'm going to start right away. And if it's false, I'm just going to kind of wait for something else. And then since I'm basically just stepping through this array, then, this is actually a little bit of over statification, if you will. But just for simplicity and to kind of keep things more or less straight. I have this array, and I want to step through the array. And so my one state variable is going to be the next index of that array. And I'm going to initialize it to -1. Why? Because then when I increment it, it's going to go to 0, and then the 0 is going to be the first element of it. So that was maybe a better way to do that would be to initialize it to 0 and then get the first one first and then increment it. But this way I increment it and then do the other. And then the other state is
inclusive of your starting point, or is the path every point after where you start you want to move?
it would be the way that I do it here is at every point past the starting point, because the mover already has its starting point. So okay, so how can I do this? And here's an event graph that does this. So now my run event initializes my state variables. This start on run is a Boolean condition that says if that's true, then I'm going to schedule an event I'm going to call it next waypoint. And what is the next waypoint going to do? Well, it's going to increment my index and then set the next waypoint to be whatever is on that path. And then it's going to schedule a move to event passing that waypoint as an argument. The other thing it's going to do is it's going to listen for an end move event, and then if there is another waypoint, which is my Boolean condition, I'm going to schedule another next waypoint. So how does that work? Well, I can use this listening idea, this sim event listening, to basically drive this. So we can kind of, in our minds, at least kind of walk through what this would look like. So first, all the run events are going to occur. Remember, and one thing to keep in mind is that the run event is the one event that does not get sent to listeners. If you think about it, that should kind of make sense. But anyway, so let's say this run event happens first for my mover. Again, nothing else gets scheduled. Then this run event will occur, and if I have set start a run to true, it will schedule next waypoint, which will set up the next waypoint for me, pass it as an argument to the move to event. And now, because my simplest mover is listening for that, it will hear a move to event with, in this case, a point 2D as its argument. And what does it do? It will simply do what it did before. It will set the destination to that argument, schedule the start move event, do all this calculation that we did before, schedule the end move event, and then it's done. When the end move event occurs now, because the mover manager is listening for the simplest mover, the end move event will get heard by the simplest path mover manager because it has one. And now it says if I have another element on my path, I'll schedule the next waypoint. And if I don't, then this next waypoint event will not get scheduled, which means that the move to event won't happen, and then the mover will just kind of sit where it is. So let's see if I can just do a context switch. Okay, so what does that look like? So here's our simplest path mover manager. So what do we have? We have an array of point 2Ds, which I'm going to call the path, and then a Boolean start on run, which is going to be true or false depending on whether I want to start right away or not. then I have two state variables. The next, I'm going to call it next index, which is the next index of my path. And I use that to kind of click along. And then a point 2D, which is going to be my next waypoint, which I'm going to just pull out of the path. Now, here, again, what I'm doing is I'm using the zero argument constructor to instantiate the next waypoint. And just initially, it's going to be the not a point. But again, the thing to keep in mind with all of these in the SimKit side is that whatever you initialize your variables to your state variables to be in the constructor, you have to keep in mind that that's not going to be where they land. The initialization of state variables is always in the reset method or in the init method if it happens to be an array state variable. So in this particular case, the only reason we're instantiating it here is just so we have the instance. I mean, I could have instantiated it here, but I wanted to be a little bit lazy and just actually here I could have just sort of set the set the location. So that was actually kind of somewhat unnecessary. All right, so let's compare this with our event graph. So we have a run method, which is going to maybe schedule a next waypoint. So let's see how that works. So here's the run event. And so if start on run is true, and just as an extra check for this, if my next index is less than the length of the path -1, in other words, if there actually is one. If I've given it a path of length 0, then this actually doesn't make sense because I'm telling you to go to a location that doesn't exist. So this is just an extra check on that. I schedule next waypoint. So I'm clicking the index, again, just following the same pattern of getting the old value, doing the state transition, then firing a property change. The next waypoint, again, what I'm doing is I'm setting the location for that as the next index of the path, and I'm firing the property change. And here I schedule the move to passing the waypoint. And here I want to use the getter because I want to make sure I pass a copy to preserve encapsulation. And then finally, here's the end move event, and basically I'm saying if now my index, if there is a next index, then I want to schedule another next waypoint. So the next waypoint method, where am I here? Yeah, is protected by the fact that the next index is actually going to be a legitimate index. So how do we run that? So we're taking the same mover we had before, and now here's the path. So so first I want to send it to the origin, and then I want to send it to this location, then this location, and then finally back. If I want to send it back to its original location, I can just simply get that from the mover, wherever it is. So whatever array of places that I want to send this guy to, I'm good with that. So I do want to start on the run because I want to test this to make sure it's happening.
Professor Buss, are you working at themes right now, or are you still just talking? Just trying to follow on the event graph.
Okay, come on. Thank you. All right, let's try that again. So did you see any of this? No. No, okay.
Mentally, I think I saw it. You're still in Probably just need to escape out of presentation.
That's weird because I'm seeing it on mine. Come on. Crying out loud. This is this is not what I'm seeing on my screen here. There you go. I mean, I was seeing it here, but it wasn't mirroring there. Why? Gremlins. Okay, so let's try this again. Okay, so here's our array of waypoints. Here I'm saying I want to start right away. My state is the next index, which is the index of the path, and then the next waypoint is actually the point 2D, which I want to send it to next. Okay, so my reset method, basically, if I'm kind of cloning the not a point, but I should probably just set the location of that. I'm initializing the next index to -1 just because I want to click it first and then get it. That could be different. I mean, there are different ways of doing that. The main thing here is that in the run method, if I'm starting on the run, then I want to schedule my next waypoint with 0 delay, meaning start right away and then go. Again, because this is the simplest one, you can envision other parameters. So another parameter might be a time, say instead of starting at 0, start it at this time. And in that case, I would schedule the next waypoint with a delay of that time. Again, you can always make it more complicated if you want.
Does anything ever set start on run to false?
Sure, yeah. In fact, I don't think I'll be able to get to it here, but if can you think of a situation where you might want it to be false?
I mean, a path isn't open and it's contingent on a path being set, or like a path being, like your array isn't defined yet?
Possibly. What comes to my mind is just that, okay, I want this thing to kind of do this patrolling or whatever it's going to be doing, but not right away. I want it to be done, maybe in 20 hours.
What I guess I'm just trying to get the distinction of is, like, couldn't you just do that with a delay?
Oh yeah, absolutely, yeah.
Without having, like, because if start on run initializes to be true when you define it, and I'm just trying to think of, like, when you would deal with a situation just either by setting the delay to 0 or just setting the delay to some non-zero number.
Yeah, well, I mean, once you start embedding this in, this idea in a scenario, then you almost always want it to be false. Yeah. And the thing is that there are some circumstances where at the very beginning of the scenario, I know I want this unit to be doing this at a certain time. There are other situations where I don't know what that time is going to be, but it's only going to be in response to another event. And in that case, if it's false, then what I can, the idea is that this next waypoint method, event, if I have another component which is going to schedule that when the criteria are met, then I can do it there. Here it's just
It's almost like a placeholder for an actual more realistic event.
yeah. I mean, there's always a little bit of tension between kind of starting as simple as possible and then building up from there and then kind of anticipating what kind of uses it might have. So, so again, these, at least as hopefully evidenced by the name, simplest, are really just more for illustrative purposes, because when we start working with them, we're going to have to make them a little more complicated. So these are more pedagogical examples of how this methodology can be applied to this, rather than, full up components that can be used in, more complicated situations. So again, this is a classroom exercise, as it were, rather than something else. Having said that, there are, if you continue on this road, which we will, at least for a little bit, or maybe I will, but maybe I'll make you do that, because that's my prerogative. There are additional things that one can basically do. But so in terms of running this, though, again, we instantiate the two of them, and then we add them as sim event listeners to each other. So here, the path mover manager is listening to the mover, and here the mover is listening to the path mover manager. I'm using my simple property dumper to make sure that the state transitions are coming out. One thing you may or may not have noticed, that there is an overloaded constructor on simple property dumper, and there's a Boolean there. What does that Boolean mean? Well, we'll see what that does. And so we're running in verbose mode. We just reset start simulation, and then when we run it, let's sort of see. First of all, we want to make sure our parameters have gotten in there, so all of our points are in there. Okay, so now we have our two run events, one for the simplest mover, one for the path mover manager. So our simplest mover, again, their state variable comes out to the right things. The path mover manager, okay, our next index is -1. Our next waypoint is not a number because we haven't done it yet. But now it schedules the next waypoint. That's the thing we're looking for. And so what does that do? Next waypoint increments the next index. So we go from -1 to 0. The next waypoint now goes from our not a point to our first waypoint was 0, the origin, just as before. And so now we see that the next waypoint has scheduled a move to, and then notice that it's the simplest path mover manager's move to. But then when that occurs, we see that the start move event for the simplest mover has happened. And furthermore, and this is where the true of the simple property dumper comes in, if that's set to true, then what that does is, in addition to showing the state and its transition, it tells you which component it came from. So what this shows is that the simplest mover's current destination has now been set to the origin, even though the event was scheduled by the path mover manager. So that shows that that verifies that the listening is happening correctly. And so now we have a start move, and so now our current destination is now the origin, and we say we're going to move there. When we say move there, our velocity again is the same as it was before. Our start move time is 0 to 0, and then our end move time is now 1.25 as it was before. But now, when the end move for simplest mover happens, that in turn schedules the next waypoint. Why? Because when the end move event occurred, the path mover manager was listening, and so the end move event was triggered here, and then that in turn scheduled the next waypoint. So the next waypoint is 3040. We click the index, get the next waypoint, schedule the move to. The move to now says, because that's heard by the simplest mover, our current destination is now that next waypoint. Now we have a start move event. We have a velocity. Okay, so now does the velocity pass the sniff test? Well, now we're going from the origin to 2 positive coordinates, and so that means that the x and the y of the velocity are going to be positive, so at least it's going in that we're heading in the right direction. We could verify, in fact, we have previously verified that 32 and 24 is a magnitude of 40, so at least that's right. And now our start move time is now whatever our time is now. And then that schedules end move, and then it just kind of keeps going and going and going until we finally end back at our last destination, which happens to be our initial location, but that's just because we made it so. Now here's where if you're approaching this with a mindset of discrete event simulation, then this kind of makes sense. If you're approaching it with the mindset of a programmer, then it kind of goes off the rails a little bit. So here we have an array. We have a set of points that we want our guy to go to. And with a programmer's hat on, how would you do that? What mechanism would you do if I want to do something a certain fixed number of times? A for loop, right? Now, why don't we do a for loop here? Yeah, exactly. In other words, remember, events happen in 0 simulated time, everything in event. So where would we put the for loop? We'd have to put the for loop in an event somewhere. And that event, everything would happen there in 0 time. So if we did that, we would, with that event, we'd say, okay, go here, now go here, go here, go here, go here, all at once. And we wouldn't have the time that it takes to get to each location. And so because we, now with our discrete event hat on, we see that we need discrete events at the right times to be located at all those different locations. Okay, so it's important to have the right context when you're kind of looking at something. So again, the natural programming approach would be, a for loop. But a for loop does not take into account the fact that time has to elapse before each of these happens. And so the way that the events work on that are that the time elapse, all the time elapses are right here, the time between when we start move and we end move. And furthermore, as you can see, at least in this example, we're going from, in this particular case, we're kind of jumping, if you will, from one location to the next, but we're not jumping in just sort of 0 time or anything else. We're jumping in the right amount of time that it takes to get there. Okay, so that there are kind of 2 more simple ones that I want to present, and I have exactly 2 minutes to do it. So I can't talk that fast, so I'm going to have to pick this up again next.